Lab 4, Oscillations. In this lab, we will compare an observed oscillation and compare it to the predicted motion oscillation from a globe script code and our tracker data of a spring in an ellipse motion. We will be analyzing three graphs: the x motion, the y motion, and energy over time. In this lab, we will be using Newton's second law for predicting future motion, spring force law, and the energy principle to make all of our computations. Here is an overview of our motion. In the top left corner, we have that our system starts from rest, and then it is let go and is traveling in an ellipse pattern. We use tracker to find all the data points from the center of mass to create an x and y list of data points. For our code, we set our initial conditions that the ball's mass is 0.402 kilograms, and we know that it starts from rest, so our initial velocity is 0, and we have our initial position listed below. We also have that our k is equal to 6.83 as computed, which I will discuss more later, and our LO or L naught is equal to 0.123, which was computed and given to us through our EDX video. We have that our L is equal to the ball's initial position minus the spring's position, and our unit L vector is equal to the L over the magnitude of L, and our S is equal to the magnitude of L minus L naught. Then we set our initial conditions for our energy, which we use from the known principles, such as the kinetic energy is 1/2 mass times velocity squared. We also have that our gravitational potential energy is the ball's mass times gravity times the ball's position. And we have our potential spring energy at 1/2 times k times the stretch squared. We have our total change of energy equal to our kinetic energy plus our potential gravitational energy plus our potential spring energy. Next, in the center section, we'll be doing a calculation loop. We have our force of gravity and force of spring as listed below, similar to our initial conditions, where we have the force of gravity as the negative mg and the y direction, and our spring force is the negative k times s times our L hat. And we then compute our F net, which is force of gravity plus the force of spring, and we use Newton's second law, stating that the ball's velocity is equal to the ball's initial velocity plus the total force F net over the mass times delta t, and we make future predictions using Newton's second law, stating that our ball's final position is equal to the initial position plus the ball's velocity times the change in time. We do this in repeat iteration, also including our kinetic energy and our change of kinetic energy, which is similar to our initial conditions. Here on the right handwritten formulas, we see that our period t is equal to 2 pi times the square root of the mass over k, and we solve for k, and this is how we found our k in our spring. We also found our initial L naught by knowing our forces acting on the system, which is the force of gravity and the force of spring, and solved out for the variables independently. And we also used Newton's second law to break down our our next position and our next velocities. Here in the graphs, we have the representation of our energy principle on the left. In the blue, we have our change in kinetic energy. And the red, we have our change in gravitational energy. And the green, we have the change in potential spring energy. And the orange, we have our total change in energy, which is 0 because of our bounded motion. On the right, we also have our x and y positions versus time, where our x is more accurate than our y position from the ellipse. So what does it mean? So starting from our energy principle, we know that the change in energy is equal to the change in kinetic energy plus the change in potential energy. Breaking down our potential energy, we have that it is equal to our change in potential gravitational energy plus the change in potential spring energy. And note that our delta E, the change in energy, is 0 because we do have a bounded system. Oscillations of the periods in x and y data, we have that our x oscillation is 1.65 seconds, which this is where we derive our first k from, and our y oscillation is 1.52 seconds, which gave us a new k of 6.87. Note that we took the same process from our previous slide to solve for our k and our L naught, and we created a new set of graphs by using the x and y data. As you can see here for the new models, there was a significant change on which K that we used. I do find this rather odd as the object is moving in an ellipse motion rather than a perfect circular motion. On the left side, on the top left and bottom left corner, we have our x position and our y position versus time listed. And on the right side, we have our y spring constant from the x position and the y position over time.